Is David, and I'll be going over this problem. So what I want to do in this problem, I want to be able to turn this into a Taylor series. So the first thing to do is to turn it into a Taylor polynomial, because we don't know how this is going to look like as a polynomial. So the first thing we want to do is let's take it to the fourth order, so to the fourth derivative. So if I take f prime, this is going to be 1 over x minus 2. And then what I'm going to actually do to make this easier to derive, I'm going to bring the denominator to the numerator. So this f prime is actually going to look like this. And this is equivalent. So we're going to base all our results like this. It will just be, so we don't have to do the quotient rule. So now we're going to take the double derivative, and that's going to be -1 x minus 2 to the -2. And then let's take the third derivative. That's going to be 2. That's going to be -3. Then we take it to the fourth derivative. This is going to be -6. Oh, and something I did forget to mention is that we're centering. No, this is not Maclaurin, because if it was a Maclaurin, it would be centered around 0, but we're centering it around 3. So A is 3. So now, if we solve for it, so f of 3, that's going to be ln of 1, because 3 minus 2, and then ln of 1 is just 0. So then we're going to have a f prime of 3, and then that should be 3, 1, so that's going to just be 1. And then f double prime, and then that's going to be 1 in the denominator again. That's going to be -1. And then the numerator, and then for the triple prime, that's going to be 2. And then f4 prime, that's going to be -6. Okay, so now we need to see, we need to try to come up with our Taylor polynomial. So the p and x. So the first term, that's going to be 0, so we don't have to write anything. Then the second term, we remember with the formula, is going to come the x, so the first factorial, which is just 1. And then it would be an x to the first. And then let's move to the second term. The second degree, so is going to be, oh, sorry, backtrack, because we're taking it the center around 3. We want to say x minus 3. And then we see this -1, so let's go to the second one. So -1, but then this would be a 2 factorial. And then it will be x minus 3 again to the second degree, to the second power. And then we go to the next one, and it's 2 to the third factorial. And then x minus 3 to the third. And then for the fourth one, it's going to be -6 -6, and that's going to be to the third, to the fourth factorial. And then x minus 3 to the fourth power. And then from now on, now the next step, we need to come up with our sum. uh, with our sum. So let's see patterns right here. So let's write the sum, and this is to infinity. So let's write the center term. So let's do x minus 3 here. We know it's gonna definitely have a fraction, and then from what we see, it should be. It depends where we want to start our k. Let's just say n factorial plus 1. So I'm gonna actually call it k plus 1 factorial, and we say k is equal to 0. So that means let's look at the denominator. So we plug in 0 for the k, it will be 1 factorial, which is just 1, and then a second term, so 1, it would be the second one. Yes, so this works out. Okay, so now let's move to the numerator. Oh, okay, another thing to note is that this series is alternating. So we're going to have a negative 1 raised to a certain power, and because we start at 0, that means we should start with the k. And that will give us an alternating series starting with a positive number. So now let's look at our numbers. So our exponents. Our exponents, it looks like it starts at 1, 2, 3. So we should do k plus 1, and that will give us a 1, 2, 3 starting at 0. And now let's look at our numerators. At the numerator at the numbers right here. So now let me do one more, because I have a hypothesis that, I have a theory that this is a factorial, but I want to double check. So let's think about this. So if I take it to another degree, so if we look at this right here, and let's say I bring it to another degree. Oh, sorry, and I forgot negative 4. So if I do negative 4 times 6, that's going to give us 24, which in a factorial, yes, that would be the next number up. So this works. So it is a factorial. And it's actually just going to be a k factorial. Because we have 1, we start with 0. 0 factorial is 1. 1 factorial is 1. Then 2 factorial is 2. And then, so that works out perfectly. Oh, sorry, and I forgot the factorial sign right here. So that should be our sum. Okay, now the next thing is, we want to see if this Taylor series, this power series, does it converge everywhere? Like, is it a perfect match, or is it just converge for one point, or is it converge into an interval? So the way to check that is we're gonna actually we're gonna do the ratio test on this. And when we take the ratio test, we want to pretty much add a 1 to all the case. So this guy is going to look like. So I take the limit as k approaches infinity, and we're going to treat x as just a number, as just a constant. We're not going to worry about it at all. So because it's the ratio test, we do an absolute value sign. So this alternating will actually just go away. So it will be x minus 3 raised to the k plus 2, because I added a 1 everywhere, it's a k. And then I go to the next one, and then k plus 1 factorial. And then I go to denominator, and I say, okay, then I add an extra one, so k plus 2 factorial. Okay, so now, because it's the ratio test, we're gonna take the original series, the original power series, and put in the denominator, and divide it by the entirely new series raised by just 1. So I'm just gonna do this right away, because when you divide fractions, we're gonna when we flip it up, it takes like the reciprocal, so it's gonna look like this. So the k plus 1 is gonna come right here, factorial, and then this x minus 3 raised to the k plus 1 is gonna come down, and then the k factorial is gonna come down. And now all we have to do is just simplify. So let's take the limit of this. So the limit as k approaches infinity. Okay, so we've simplified. We see. Okay, let's start off with this. Let's start with this right here. You can start really anywhere. We see that we have one extra. So so when we're dividing numbers, we subtract their exponents. So if we say, okay, so what is k plus 2? I'm taking the exponent of the x minus 3 minus this other k right here, minus k plus 1, but because a negative minus 1. So these two k's cancel, and we have 2 minus 1, and that's just going to be 1. And so we have an x minus 3, and that's it. We don't have all the exponents went away. So what I like to do, so I don't get lost, just cross it out like this. So now we're left with all the factorials. So if we expand these factorials, we can do that because these factors represent a huge change in numbers being multiplied. So you have k plus 1 factorial. Look, if we think about this factor in the denominator, the k plus 2, there is already a k plus 1 and all the numbers of the k plus 1 factorial. So this k plus 1 factorial can actually be eliminated. And in the denominator, we're just going to be left with a k plus 2 because that was the only thing left when we simplified it. So now if we look up top and we see the k and then the other k, if we think about this, there's already a k factorial in the numerator. So this k factorial and everything with it actually just cancels out. And we're just going to be left with a k plus 1, right? Okay. So, and that's completely simplified. So now it's easy to take the limit because if we just take this case and compare their exponents, the exponents are the same. So because they're the same, this whole thing can just be crossed out, and our limit of this thing is going to be x minus 3. And because we're doing the ratio test, in the ratio test, if it's less than 1, it converges. So if it's less than 1, it converges. So now we want to come up with the convergence radius, with the radius of convergence. Now we know that it doesn't converge everywhere. Now we know it doesn't converge just at one point, but converges in a certain amount of points. So if we take the center, right? This is the center, and that means this became our radius. The 1 became our radius. And the way the intervals, I always like to draw a number line. So we have a number line starting at 3, not negative 3, because that's just how the Taylor polynomial is structured. You have the center as the negative. If it was a plus, it would be a negative, but it's a minus and it will be a plus. It's kind of trying to solve for 0. So okay, so now we have 3, and then because it's the radius, we go right 1, so it's going to be 4, and then left 1, so that's going to be 2. Okay, so now we need to test out if these endpoints are included in the radius of convergence. and after that we will be completely done. So to test that, we need to grab, let's start with 2. So if we say that x is equal to 2, right? What we should do is now we're going to actually use this x that was in the original power series and plug it in. So it's going to be negative 1 raised to the k, and then we have that 2, and that if we put a 2 in that x, that's going to be a negative 1, and negative 1 to the k plus 1, k factorial. We'll just write the whole thing out. Okay, so now let's analyze this. So if we simplify it, if we simplify this power series, which we can, oh, you know what? And look what we could have actually done. We could have actually simplified this sum a little better, and I'm gonna do that right away. Because if you notice these factorials, they both have a coefficient of 1, right? So this, what is really happening is this k factorial is actually going to go away, and then we're just going to be with a k plus 1, and then this negative 1 right here is raised to the k times negative 1, k plus 1. Because they have the same base, we can just add the exponents. So we say k plus 1, we have negative 1, 2k plus 1. And this formula, the 2k plus 1, you can notice that that number will always be an odd number. If it's always an odd number, it will always be negative. It will always be negative. So the way we can do this, we can apply to see if this is going to converge or not. We're going to apply some rules of infinite series and see if it converges. So let's do a comparison test. So a comparison test, the best number that to compare it to is honestly just the sum of 1 over k. And then if we notice this 1 over k, it's actually just a p-test. And the p-test is 1. So p is equal to 1. When p is equal to 1, it's actually just going to diverge. It should diverge. Now the next thing, just give me 1 second. Okay, so yeah, so it's going to diverge. So because we compare it to that, I think the best thing to do is to do a limit comparison test. So we take the limit of, I always like to put the sum that I know first, if it converges or diverges, in the numerator. And then the next one in the, we can just write negative 1. Is the same thing. So now, if we do this, if we take the limit, we take the reciprocal, so it's gonna be the limit as k, negative k, I guess, and then k plus 1. And then we see that this value is actually just negative 1, and if it gives us a value, that means this series does diverge. So this 2 is gonna diverge. So we put this little thing right here. So now we just have one more, which is the 4. Okay, so the 4, we're gonna plug it into the original series, and you know what? Going up here, from what we see our original series, how we wrote it, and how we simplified it, I think I'm just gonna stick uh, with the simplified version because it's just easier. So we said that yeah, the x is equal to 4, right? So we have a negative. So if we plug a 4, we're gonna have just a 1, right? A 1, and a 1 is not really gonna do anything. So we're just gonna be left over with a negative 1 to the k, and then it will be a k factorial, but we simplify that and it'll just be k plus 1. And so now this just becomes an alternating series. Because it's an alternating series, we have to do an alternating series test. So if we take the limit, if we take the limit of just I call this, there's technically a 1 right here. I call it the a sub k. If I take the limit of a sub k, which is just this right here, as k approaches infinity, we see that this is actually going to approach 0. And now, this is holding up to converge for now. So now we need to think, so now everywhere there's a k, we're going to see if it's actually smaller. So this is the way we do it. So if we take the limit, no, sorry, we're going to compare it. So we're going to take the f sub k, and then we're going to add an extra 1 into this series. And which one is bigger? Well, the one k plus 1 is bigger. So that means this one is less than this one. And this is because the denominator is going to grow in this function, in this series is going to grow even faster. It's going to grow even smaller than this one. So yes, it is smaller. So that means this point should converge. So that means in summary, our final result should be that the Taylor series for f of x equal to ln x minus 2. We write, if we take the simplified version, which is just negative 1 to the k, and then the k factorial, that will simplify it, so it will be k plus 1, and just as an alternating series, as k equals 0, and as infinity, and then our radius of convergence is 1, and our intervals are from 2 to 4. But we put a bracket on the 4 because we include it. But I did forget something. We do include this x right here, so we have an x minus 3 because it's our center, k plus 1. So I'm going to zoom out in case that was a lot of work, but this should be our final answer right here. Okay. So that's pretty much it. It's just if I had to summarize the whole problem, oh, sorry about that. Sorry, if I had to summarize the whole problem, I would just say the first step is to, the first step is to take the original function and derive it until you can see a certain pattern. Build your Taylor polynomial until you can see a pattern to build your Taylor series or your power series. And now you have half of the problem, and then you need to say, oh, is this going to converge everywhere in just an interval or just in one point? Or is it just true for one point? So, you take the ratio or root test, but we didn't really need to do the root test. The root test is not very common. But if it comes up, I would very much recommend that. And then see what you get as your radius, and then see the intervals by doing the number line, and then at the very end, um, just test them, plugging them in for x, and then try out different infinite series tests to see if it converges or diverges. So yeah, that's basically it.